And, you described me as sort of a Bayesian critic or but, I don't think of myself that way. I'm just, I'm non-doctrinaire. So I think different tools for different problems, and I'm open to seeing what's good and bad about every tool. But there are, I think in causal inference, there are some unique challenges. My talk, I guess, will be sort of the inverse of Phil's in some sense. But so I'll be interested to see what Phil has to say about all this. So here's my outline. I'll do a little bit of background on causal inference, just so we're all on the same notation and so on. I gather everybody here is quite familiar with that stuff, but just want to make sure we're all kind of on the same page. And then I'll actually talk about two problems. So one of them, which is where the Robbins-Ritchoff result comes in, is about estimating causal effects. And so we'll talk about that. And then if there's time, I actually don't even remember how long I'm supposed to talk, so you just cut me off whenever. But if there's time, we'll also talk about a little bit about causal discovery. This is to be a little bit of a equal opportunity person, because I'll be just as critical of frequentist inference here, because I just think the problem's so hard that both modes of inference have serious problems there. I don't know if I'll get to that or not.
With 35 minutes, by the way.
Okay, so I should finish at like 1:30 or 1:35 or something?
Yeah. And then we'll have 10 minutes of questions.
Okay. So the background is, we're having, as usual, we'll have some IID sample from a distribution P, and we want to estimate some function of P. So I haven't even got to the causal stuff yet. I'm just saying in general, what's distinguishing causal inference, I think, or other problems from many other, say, machine learning problems, is that we're not interested it's not just a predictive thing, is that we're interested in some feature of the distribution P, a function psi of P. So an example would be, even the mean of P, causal effect is a special ordering. The causal ordering, or DAG, would be a very complicated function of P. And the point here that I'll be talking about is that, getting a point estimate is not enough. We want some measure of uncertainty. And the point of view I'll take in the talk is that we would like a confidence set, and that's something we can, obviously people can debate, but it is one form of uncertainty quantification. And so we're going to want, the nice thing about a confidence set, though, is that there's a kind of a objective, so to speak, test of it, which is at the end, you want to prove that the parameters contained in your confidence set with probability 1 minus alpha, at least asymptotically. And this is something, you can check, right? We could simulate it and see how often does it contain the true value. And so there's a kind of a well-defined bar that we have to reach, what prevents us from doing sort of somewhat arbitrary things. So, of course, the Bayesian approach would be quite different, which would be to put a prior on the distribution P, or if you prefer, we can think of P as being indexed by a parameter. Maybe it's finite dimensional, maybe it's non-parametric, and put a prior on theta. These are just different ways of writing the same thing, that we'll have a prior on a distribution. Then we would get a posterior, which I'll call B for Bayes. I think a lot of the confusion, in my opinion, about Bayes and frequentist is because we use the same symbol P. We just use P for frequencies and B for Bayesian. We wouldn't expect them to be the same. So we'll get the posterior B, and that, of course, induces a posterior for the parameter of interest psi. And so we have either a confidence interval for psi or a Bayesian posterior distribution for psi. Okay, and of course, in the Bayesian framework, we can also find a set C, which has posterior probability 1 minus alpha. But there's no reason why B of C, the posterior probability, should equal, of course, P of that thing. And in fact, in complex problems, they typically aren't equal. How often that, if we were to simulate our problem, we would see that our Bayes thing would not contain the truth 1 minus alpha of the time, nor is it supposed to. It's a Bayesian posterior interval. It's not claiming to be a confidence interval. They're just different. So what is the traditional frequentist way of dealing with inference for a function of P? These days, the standard thing to do, which has become pretty much standard, is to split the data into two pieces. This is for complex problems I'm talking about. You estimate the distribution from the first half. So your estimate might be this should say P and hat, might be the empirical distribution, could be a Bayes estimate, it could be a kernel estimate or whatever. And the key is that when you're estimating a function of P, you don't use just the plugin. So it's tempting to just insert P hat into the definition of psi. Like if psi was the mean, this would just be the mean of the data. But it's pretty standard now that you add this average from the second half of the data, from D1, where psi is something called the influence function. If you're not familiar with an influence function, it's just some function we can analytically compute. It depends on the functional psi. And the reason for doing this two-stage thing, where you separate the estimation of the distribution and then you add this correction, is that's what makes the frequentist inference valid. That under some conditions, you now get that the estimate psi hat is normal, which you wouldn't have gotten if you just used the plugin, and it's centered at the correct value. That is, root n psi hat minus psi converges to a normal with mean 0. There's no asymptotic bias here, which means, if you simulated your confidence interval and plot it, you'll see that it's wobbles around, but it's centered around the true value. So this is kind of, I would say, standard, and there's many improvements of this. You don't really, in practice, people don't just split the data like that. They split it in many pieces, you average over the splits and so on. There's all kinds of variations of this, but this is kind of, I would say, the one slide summary of standard now frequentist inference for functionals, including causal effects. Whoops, let me make my screen a bit smaller so you can see it there. Okay. This is just writing down the fact that now we have a confidence interval. And it's nice thing about this too, it's pretty simple, right? You end up just computing an average. And again, it's very instructive to do this. And I've done this a lot, where you simulate it and see, does it really contain the true parameter 95% of the time. So let's specialize this to causal effects. So the terminology I'll use is we have an outcome of interest Y, we have a treatment A, and we've measured a bunch of confounding variables. We're in the observational study situation. Now, I don't think Phil will like this, but I'm going to use the counterfactual language. There's some people prefer structural equation models. Some people prefer the do language that Pearl uses. They're all, Phil will talk about the decision theoretic way of representing things. For the most part, they're all mathematically equivalent. It's just a matter of notation, and I do like this. So this is Y of A is the counterfactual. It's what Y would be if I could set big A equal to little a, if I forced everybody to take dose little a. And then what's the form, assuming making lots of assumptions now, and in particular that we've measured all the important confounding variables, it's well known that the causal effect, the mean of this counterfactual, which I'll write psi of A, or in Pearl notation would be mean of Y given do A equals A. It's just given by this formula, which is the integral of mu over X, where mu is the regression function. So this is in the statistics causal world, we call this the G formula. That's what Jamie Robbins called it. It's called the adjusted treatment effect, the do formula, whatever you want to call it. But the point is that it's not an estimate of the distribution, right? It's an estimate of some functional of the distribution. So it's exactly that situation we were talking about. So it's a semi-parametric problem, is how we would usually refer to it, meaning that we're interested in this number, psi of A, and the rest of the distribution is considered a nuisance parameter. It's an infinite dimensional nuisance parameter. And the challenge from the frequentist point of view is to come up with a confidence interval that at least asymptotically has the correct coverage, such that if we imagine repeating this, or if we imagine many different people using this procedure on different problems, that we would trap the true value 95% of the time. So let's just, for simplicity, take A to be binary. And if we, so what are some common estimators that have good properties? Traditional or frequentist, whatever, I guess I'm using them interchangeably. A common one is the plug-in estimator, where you take the regression function, and because psi was the average of the regression function, you average it, but here A is fixed and you're averaging over the x's. But to get a valid estimator from the Frequentist point of view, remember, you do need to use some sort of sample splitting so that mu is like, say, a non-parametric regression estimator from the first half of the data, and this is computed on the second half of the data. And this gives you something which is asymptotically normal. Another common estimator is called the IPW, inverse probability weighted estimator. It's here you estimate the density of A given X, which people usually call the propensity score. So this is pi of A given X, again, estimated from another part of the data. Then you form this sum. And this is also a valid estimator under certain conditions, and it has a normal distribution and so on. The most common estimator these days is what's called the doubly robust estimator, which is sort of a combination of these two. It's an average of this regression function plus this term, which looks like this IPW thing. And the reason why people like this estimator is it's got all kinds of nice properties. It converges at a 1/√n rate to the true value. It has a normal limiting distribution. We can get a confidence interval very easily. And it's actually what's called the semi-parametric efficient estimator. It's the optimal estimator. And it has this property, which is called double robustness, which means that if your model for mu is right or your model for pi is right, either one, you'll still get a consistent estimator, even if the other model is completely wrong. That's why it's called doubly robust. So for each of these estimators, whichever one you use, the point is that computing a valid frequentist confidence set is very easy. And then provably we have, and of course there's regularity conditions and so on that won't discuss here, that we do have at least asymptotically the correct coverage. And as I said, the doubly robust estimator is optimal. But now, so I'm working my way up to this Robbins-Riddoff result, let's consider a randomized study. Suppose that I've randomized A, possibly in a way depending on these covariates X. So what changes is that this propensity score, the probability of A given X, is a known function. So it's something we've created, right? We know this. This is some known function. Okay, well, what changes? Well, let's look back at one of those three estimators. I'll focus on the IPW estimator. We don't have to estimate pi anymore. We can just put in the true value. And so look at this estimator, and it's worth noting a few things about it. It's very simple. It's just an average, right? We have I, a yi. This is just an indicator of whether A is equal to this particular value of A. And this is the known function pi. So this is a very simple estimator. There's no modeling assumptions at all here, right? We're not estimating a regression function. We're not doing any estimation of any functions. It's just dead simple. It's root n consistent. Again, a confidence interval is very easy to construct. So it couldn't be simpler. And so this is the statement that it's converging to a normal and that we can construct a 95% or whatever, 1 minus alpha confidence interval very easily. So we give a point estimator and a measure of uncertainty, which is verifiable, right? You could simulate this and check it. That's what I mean by that. So it has correct coverage. You could even get a finite sample confidence interval, by the way. I just wrote the asymptotic one because it's simpler. There's no modeling assumptions at all. And psi hat minus psi again is about 1/√n away. Notice I didn't say anything about the dimension of X, so there's no cursive dimensionality going on either. So let's now take this problem from a Bayesian point of view. So the unknown thing from a Bayesian point of view is the joint density, let's say X, A, and Y, which I'll write as P of X, and pi of A given X, and then P of Y given XA. Now the middle one we know, right? That's not actually an unknown thing because of the randomization. So the likelihood function, if I multiply these together, I can drop the pi of X. It's just a constant, right? The likelihood's only defined up to constant proportionality. The unknowns are P of X, that's like an unknown function, and P of Y given X and A. So we could say that the unknown parameters here, I'll just call it theta, are P of X and P of Y of X given A. And you could treat this as a non-parametric Bayesian problem and take non-parametric priors on these, or you could put parametric families here and just put parametric priors, either one. And then we have a likelihood and we have our parameter and we do Bayes, okay? So the prior on these quantities, and then we have a likelihood, we get a posterior for theta. Once we have a posterior for theta, we can write down the quantity of interest, and I'm just writing out again the G formula. This is expressing the causal effect that we're interested in. It's just some complicated function of the unknowns, right? So I can just take my posterior for theta. Let's just imagine doing an MCMC. I could just draw theta from the posterior, and every time I draw theta, I can compute this quantity, and I'll get a draw of psi. And so this induces a posterior distribution for the causal effect. Okay, now finally I can state the Robinson-Ritov result, which is unlike the, say, the IPW estimator I wrote down on the last one, or some of the other estimators, this thing cannot be root end consistent. It's going to converge very slowly. In fact, if you imagine the dimension of X getting larger with sample size, the Bayes estimator won't even be consistent in the frequentist sense. So if you simulated this, you'd see the posterior cannot concentrate around the true value. And that's because of these nuisance functions, which even if they're parametric, they could be high dimensional, but we're treating this, let's say we're treating this non-parametrically. This is an infinite dimensional nuisance parameter. And you can see that the 95% posterior interval will not have 95% coverage. So what's going on? Why is that happening? So this is just a place where Bayes and frequentists happen to diverge. What's going on is their theorem says that any good estimator, and there's a technical definition of that, which we won't bother going into here, but at the very least, we want it to be root end consistent, has to be a function of these quantities, pi of a of I given xi. But these are called ancillaries. That is, there's no parameter in here, right? These are just numbers. We know these things. So they're not going to show up in a Bayesian answer. When we do Bayes' theorem, these are constants. And when you multiply the likelihood, constants just drop out, like they don't show up in the posterior. Because remember, this is in the randomized case where this is known. So these numbers drop out from Bayes' theorem. And the result is that the posterior will never be a function of these things. And so their theorem implies, therefore, the posterior can never be concentrate quickly around the true value. Now, there have been attempts to sort of do what I would call, I don't know what to call it, but modifying how we think about Bayesian inference to force the posterior to include these things. I used to have a blog many years ago, and there was I had a blog post about this. There was a lot of controversy, and people argued about this. The blog was called Normal Deviate. So if you want to search it, it's still up there somewhere in the internet. There's some interesting discussion, had a little bit of a interesting discussion on that with Chris Sims, who's a well-known econometrician. But my view is if you're going to start twisting and turning Bayes to get the frequentist answer, then why are you doing Bayes, right? What's the point? I call that frequentist pursuit. If you're just chasing the frequentist answer, you might as well just do frequentist inference. So I think my view on this is you just have to accept the fact that the Bayes and the frequentists are going to do very different things, and you should decide which one you think is better to do. Personally, this is a place where I would say, somehow, I'm not saying frequentist coverage is the most important thing in the world, but the fact that if you're going to go through life producing these intervals and they never contain the true value, there's something not scientific about that to me. But you may feel differently. I mean, again, I'm not telling people what they should do here. I'm just delivering the news, right? That it's just a fact that the Bayes answer, at least as we usually interpret Bayes, is not going to have the correct coverage. Also, by the way, just as a practical matter, you need a model for that P of y given x and a. We didn't need any models for the frequentist thing. And my view is we often do need models. That's just part of statistics. But if you have a situation where it's very easy to estimate something without assuming any models, that just seems like a win to me. So in a nutshell, that was pretty quick, but that really, is the essence of that Robbins-Ritov theorem. By the way, if you've never seen it, I really encourage people to look up the original paper. I'm sorry, I should have put the reference there. It's Robbins and Ritov. I'm sorry, I don't remember the exact year, but if you just Google Robbins-Ritov and the word cursive dimensionality, you'll find the paper. It's a really nice paper. And they talk about this in great depth and in much more detail, obviously, than I'm talking about here. But I'll use the rest of my time to stray a bit from my assigned topic and just talk about what I would say is the difficulties of inference and causal inference. More generally, another part of causal inference, and here I think everybody has problems. It's nothing. I want to just say that frequentists, Bayesians, it doesn't matter, and I see this being ignored a lot, which is why I want to mention it. The problem is this. I'm sure many of you are familiar with this, which is estimating causal structure. So I give you a vector x consisting of x1 to xd. These are not different observations, right? This is the d covariates. And because I assumed right now so far that in some sense I didn't mention any DAGs, but I assumed that the DAG was given, that we had x followed by a followed by y. It was a very simple structure. The causal discovery problem is to say, no, I have all these variables and I want to discover the ordering. Very, very difficult problem. So one way you can say I want to find the causal DAG, or another way to say it, which is equivalent, essentially equivalent, is to say I want to find a permutation that puts them into the causal ordering, the correct ordering. That's a bit of an overstate because you don't need the whole permutation, but let's just say you want to find the causal permutation or the causal DAG. Now the problem, well, the first problem is that this is not an identified parameter, which means that even if we assume let's assume there's no unobserved confounding variables, then it's well known that the causal ordering isn't identified. That is, even with an infinite amount of data, the data tell you nothing about the causal ordering. This is kind of a trivial fact because let's say there's 3 variables. Of course, I can write p of x1, x2, x3 as I could write it as p of x1, p of x2 given x1, and p of x3 given x1, x2, or I could start with 3 and then 2 and then 1. And these have the same likelihood. You know, if I form the likelihood this way or this way, it's identical. There's nothing in the data that's going to tell me that one ordering is right or not. And the way this problem is dealt with, if you want to do causal discovery, is to add some assumptions. Okay, so we're going to need to add some assumptions, and there's various forms of these assumptions. Things about lists of conditional dependence assumptions, or simplicity assumptions, or sparsity assumptions, or assumptions about variances. Just for simplicity, let's take one of them. I'm going to assume what follows a kind of sparsity assumption as just as an example. It doesn't matter. But the idea here is that if I gave you an ordering, we can write down a structural equation model, and we might assume that the correct ordering has some sort of signature, that it has some sort of property. So that's fine. If we, if it's an assumption is an assumption, if we're willing to make that assumption, and I'm not taking a view on that, I'm just saying, suppose you do make that assumption. The problem is, and this is my problem in general with causal discovery world, is people produce an estimate of the causal ordering and declare victory. But point estimates are never useful by themselves, right? We want some measure of uncertainty. What we'd really like is some uncertainty quantification, like a confidence set for the ordering, a confidence set of permutations, either Bayesian or frequentist. And as I'll now explain, whether you're a frequentist or Bayesian, getting a non-trivial confidence set is extremely hard. The problem is actually mainly computational, and I believe that it's unsolved and that there's been some progress about making smoother versions of causal discovery and so on, but they don't solve this problem, and I'll explain why. So imagine somebody for the moment, an oracle gave you an ordering, pi. And let's suppose, just for simplicity, that everything's normal and linear. Then once you have an ordering and everything's linear, the causal ordering is really just a structural equation model, which just means a set of ordered regression equations. So x1, we have x1 first, then we have x2 is just a regression on x1. x3 is then a regression on x1 and x2, and so on. Every x is a regression on the previous guys. And this defines a triangular array of beta variables. So in other words, if you were to give me this normal, or actually all we need is the covariance matrix of the normal. So if you give me an ordering pi, and you give me a covariance matrix sigma, we could now unwrap and figure out what the corresponding beta is. Every permutation pi, all d factorial guys, give me a different beta. And again, they would all be equally, they would all fit the data equally well if we don't have an extra assumption. So people usually make some sort of extra identifying assumption that if I tried every ordering, the true ordering would somehow stick out to me because these betas would be perhaps sparse or something like that. So here's an example of an identifying assumption that's commonly made, and other ones are again, different, but have a similar flavor, which is that imagine you gave me a pi and a sigma and I computed the betas, and I'll measure some notion of simplicity. Let's just imagine some sort of sparsity measure, like the L1 norm of the betas or the L0 norm of the betas, some measure of sparsity or simplicity. And I could do that for every pi, and then we're going to just assume, this is the identifying assumption, that the true ordering is this, say, the one that minimizes that. Okay, that's an example of the type of assumption that's made. Again, there are other ones involving conditional dependence or variances and so on, but we'll just focus on this one, doesn't matter. The point being that that identifies pi now, because what we've done is, if you give me a sigma matrix, then in principle, and we can certainly estimate sigma, that's just the covariance matrix of the variables. In principle, I can estimate sigma, well, of course I can estimate sigma from data, and in principle I could try every permutation, compute the corresponding beta, compute its sparsity, and find the one that minimizes it, and I now have an estimate of the true ordering. So in other words, we've really defined a mapping through this assumption that takes any sigma, any covariance matrix, and maps it to the true ordering. Now the big problem is this: you give me a sigma, to find the true one, I have to try all d factorial orderings. And as I say, there's been some progress in trying to find ways of improving these calculations. For example, you can enlarge the model and make a continuous function that includes things that aren't DAGs, and the DAGs are just special cases. But that thing still has d factorial zeros that correspond to the DAGs, and it's not just NP hard. It's like it's d factorial hard, whatever that the official term is for that. So even if I even forget data, if you told me the true sigma and I tried to find the true pi, there's nothing, I don't know of any way around having to try all d factorial orderings to find the true thing. You can make even further assumptions, which some people do in this world, which assures that a greedy algorithm will return the correct ordering. But that's not going to help you with the next step. So the confidence set, and this is again whether you want a Bayesian or frequentist. In principle, we can construct a confidence set or a Bayes posterior for this very easily. Sigma, the covariance matrix, is a pretty easy thing to estimate. We can construct a confidence set or a posterior set for sigma. There's many ways to do it. Let's just suppose I construct a confidence set for this covariance matrix. In principle, I could now take every sigma in my confidence set here, find the corresponding pi, which involves a d factorial calculation for every single one in the confidence set, and collect together all of these pi's, and that's a valid confidence set or a valid posterior for doing Bayes for the ordering. Okay, but I've never seen someone do this. I mean, you could, if you have 5 or 6 variables, you could do this by brute force calculation. I suspect that even if you did it for a small number, and I'm just conjecturing, that this confidence set will typically be huge. That even with not many variables, you're going to be disappointed in how many pi's are contained in there. I don't have a proof of this, but that's just my guess. But if you could do this, at least computation and overcome the computational issues, at least you would have a valid either confidence set. But again, I really see that the difficulty here is the combinatorial search for computing the confidence set. Again, there are ways around this to get just a point estimate, where people will do greedy things and cross their fingers. But for a confidence set, it's much trickier. And again, the set might be huge, although I've never seen them compute that. Same thing, if D is fixed and N is large, then that's a place where Bayes and frequentist things agree. So the Bayesian posterior would also have correct coverage. And you could now do an MCMC approach where you'd sample sigma from the posterior. For each sigma, we would compute the pi that minimizes that simplicity measure or whatever we're using and get a posterior. But again, for every draw, you have d factorial calculations to do here. Unless, again, you add even further assumptions so that your whatever algorithm you're using to do causal discovery is guaranteed to find the minimizer. But that's a set of further assumptions. So it has the same problem then as the frequentist set. Okay, good. So I'll finish right on time, I think, here.
Perfect.
So yeah, I'll just do my conclusion. So let's not, forget what the attraction of Bayesian inference is. It's, first of all, I think it's very easy to do in some sense. So the frequentist thing, I kind of said we have a way of doing it if you compute this thing called the influence function. A lot of that stuff's not easy to do in general. And so I didn't want to make it seem like that's a trivial thing to do. So it can be very difficult to do it. Bayesian inference has this nice generality, right? If you have a prior that you think is reasonable, then you can just turn the crank and compute the posterior and run an MCMC. So it does have this nice attractive property that's quite general and in some sense easy to do. I mean, of course, MCMC can be challenging, but at least we know what to do. But it is true that in complex problems, those Bayes estimators are not going to be optimal. And the confidence intervals just won't contain the true value with the right frequency. And that gets into a philosophical debate. One attitude is to say, well, I don't care about frequentist coverage, so I'm not going to worry about it. But if you're estimating the causal effect of vaccines on COVID or something really health-wise important, and you're doing this for lots of people under different situations, and your intervals never contain the true value, you have to put the dogma aside. And it just seems to me that that's kind of, if nothing else, it's a robustness property of Bayes that you'd like to have, that at least the frequentist coverage should be at least approximately correct. And that's just going to fail in these complicated problems. So personally, ignoring frequentist coverage is not a good idea. One thing I do like, which would be a whole different talk, but I do want to mention this, something I find very interesting is, can you combine frequentist and Bayesian ideas? I think, why not get the best of both worlds? Bayes allows you, for example, to include valuable prior information if you have it. And there are ways of doing that. And I'll just mention two that I've found very interesting recently. So Peter Hoff and his collaborators do something they call FAB, which for people of my generation reminds us of the Beatles. But it means frequentist and Bayes. And it's a way of combining frequentist and Bayesian inference. I won't get into it. Obviously, I don't have time here. But I would suggest you look at that paper. I think it's really interesting. It's sort of a way of, you get to put in Bayesian prior information, but still get good frequentist properties. And I actually have a paper recently with my colleagues, Adi Ramdas and Siva Balakrishnan, where we do something called universal inference. It's a fairly general way of getting exact confidence intervals and frequentist inference, but there's a lot of options in what you can. It allows you to take a kind of arbitrary estimator and get a valid confidence interval, and that estimator can be a Bayes estimator. So in a way, it allows you to use Bayesian tools to get the estimator, and but then on top of that, you can still get a confidence interval with valid frequentist inference. So I know that there's always a lot of division in statistics between the whole frequentist Bayes thing, and now we see it in AI and in machine learning. And I have to say, I've also seen it in, I work a lot with physicists. I see it in astronomy. I see it a little bit less so in particle physics. So I've seen it there. I've seen it now recently. Well, you see it all over the place. And, maybe I'm being naive, but I think bringing these things together in various ways is something that deserves more attention. So that's the end of my talk. Thanks for your attention.
Thanks very much. Are there any questions? Maybe I can start with one. Actually, is it possible to bring in, when you start doing the factorizing the model out with like pi a given x, etc.? Because I think those slides are really nice to talk about. But my question was like around the what is the properties you need on A and X for this sort of scary, to a Bayesian, a scary result to hold? Like if I'm building a recommender system and I know my actions are discrete, even if there are a lot of them, should I be worried, for example, does this theorem hold, and is it going to cause me pain?
Yeah. So if everything was discrete, but you have a lot of categories, then that behaves essentially like a non-parametric problem for all practical purposes. So if you think of the number of categories as being D, If D is large relative to the sample size n, then this, basically the same theorem will still apply.
Okay, so it is you're in favor, but I think maybe that this is your addition at the start circumvents this, but if there are something, perhaps it seems to me a weakness of it is you need exact coincidence. If you're using an IPS-based method, you need to have seen. I actually can like to rephrase it in terms of like your Y, I think, was reward, your A is action, your X is context. I think that's how a recommender system person would formulate it. And you would need an exact coincidence between an X and the A. It turns into something that looks, I think, like clicks divided by expected impressions. Is that a fair summary? And why not clicks divided by actual impressions?
So I actually didn't quite understand the question. So the estimator, yeah, it requires P of A given X is known. That's some known function by assumption.
Yes, which is like you're randomly doing actions. We call that a policy usually.
Okay.
And we'll then look at past knowing an old policy, which becomes I think usually it's the pi zero. I forgot your notation. The IPS score, you're dividing by this, which it turns out, if the A is to show a recommendation, it's in advertising, computational advertising is the use case I work on, it's an impression. So it becomes, if it's reward and on the numerator, your Y is a 0 or 1, you're simply counting how many times. So you're looking for, you're matching in history how many times this happened. And if there's any slight variation, there's no match. So you can end up with not many matches if you're going over history like this. Does that make sense?
Yeah, I see. Yeah. So first of all, that estimator, right, is just one particular estimator. In fact, it's not the optimal estimator. So I just put that one down because it's simple. So there's other estimators. In fact, the doubly robust estimator is the one people would use in practice. The point, though, is, what the theorem says is whatever your estimator is, if it's not a function of the PA given X's, then it can't be root inconsistent. So the key is whether the pi A given X appears somewhere in the formula or not. That's kind of the heart of the theorem.
Okay.
Oh, I have a question. Hi, Larry. So, so this may be a naive question. I think I'm finally understanding a little bit of this problem. So in my naive way of seeing the problem, I would probably draw a DAG where I would have the high dimensional X pointing to a low dimensional covariate pi I. So I would think of the propensity as a variable instead of as the density, even though it is, and then pi I pointing to AI. And then in my naive way, I would look, well, I can either condition on Xi or I can condition on pi I, because pi I blocks the backdoor. And then I would identify the estimand and do Bayesian estimation on that estimand. So would that not be a pure Bayes of doing things, or would it be wrong? Does that make sense? I'm not sure if it makes sense to the question.
Yeah. No, it's exactly. So in that blog, that was exactly what one of the things that several people talked about, including, I think Chris Sims might have mentioned that. It's not, I mean, if you just take the data and write down Bayes' theorem, that's not what you'll get, right? So you're doing some
causal inference before doing the Bayes.
Yeah, you're doing some sort of transformation, which is not, and again, I'm not saying it's unreasonable because it basically gives you back the answer I had. But then where's the Bayes? I mean, I just sort of feel like if you'd never thought about this problem and I just gave you the data, that's not, one would just write down the posterior and get the posterior. Then you notice this problem, and then you kind of, you have to forget part of the data, so to speak, and then compute the posterior, which is fine. But again, that just feels to me like if all we're trying to do is redefine what we mean by the Bayes estimator to get the frequentist answer, congratulations, you're a frequentist. I mean,
Oh,
it's,
yeah, no, I guess I don't disagree
it's
with
fine.
that.
I'm just sort of differentiating it between, how people usually, what they usually mean by computing a Bayes estimator. But yeah, you could certainly do that. Whether you want to call it Bayes or not, I guess, is a debatable thing.
If you're using the propensity score, would you agree that then you're violating conditionality and then it's not Bayesian?
Well, that's what I would say, but that was, again, what a lot of the debate was on my blog was, is that qualifies Bayesian or not? And I guess everybody has their own opinion about that.
So in your view, the purest Bayesian way out of it is to say, I just don't like the frequentist property and I'll live with it. And I like the Bayesian theorems that say certain things are going to behave well. And I just have to accept the poor frequentist coverage properties here.
I guess I'm trying my hardest to not be prescriptive here. I guess I feel like what we would usually call the Bayesian answer would be just what you just said. Yeah.
Any further questions? What about Bayesian convergence? Like, does it not come to play here? Why? Because there are quite good theorems. I'm not a theorist, but they seem to be quite good theorems. Does this somehow override them in this particular setting? What?
Yes, this is precisely an example where they fail. So the Bayesian Bernstein von Mises theorem, that with the posterior converges at a root n rate, it fails here. So this is because it's a semi-parametric situation.
So when I talked about things being discrete, etc., like actions discrete, presumably actions small and discrete, you're okay. If everything's discrete.
Yeah. Oh yeah. If everything here, if everything was discrete with a fixed number of categories and n gets larger, then there's no problem.
Okay. But at some point, as things get, I remember there being conditions on, say, pi being quite rough, and the marginal on x being quite complicated. I couldn't. Yeah. From a practical point of view, I couldn't read whether that. I mean, the paper seemed to argue this is a normal situation, but I was unable to understand if that was actually the case, that sort of practical people had to worry about it or not. Yeah,
their point there was that, if you make enough smoothness assumptions, you can make the problem go away. But smoothness is a dimension-dependent-ish thing, right? So what seems smooth in 2 dimensions, like say 2 derivatives, feels smooth to us. But when x is high dimensional, 2 derivatives is not smooth enough to get good results. So all that stuff about the roughness and everything is pointing out that smoothness assumptions won't save you here when x is high dimensional.
Okay, interesting. Do we have one last one, or should we just say thank you? Well, thank you. That was super interesting, and we're really grateful to start us on one of the negative or like contrarian note with both Bayesian and non-Bayesian approaches to causality. So nobody has it easy to start with. Thank you so much. It's another problem with Zoom is we can't do proper applause, but thank you. It's